And these were the answer for this Irodov question. Now this is a very interesting question which also makes us think about the two rotations which are combined, and there is also a CRTM, rolling motion. Then how we are going to approach? The concept here what we discussed is relating with this question, so that's why I am discussing this. Okay, I have discussed that question. Now let's dive in this question. For you, if it is becoming boring, then you can of course watch it in the two parts. So let's go to this question number 7. You can also watch other videos as well. There are the other videos on the other topics in my channel. You can watch, and if you feel, you can also subscribe to my channel. Let's go. So here what is given is two thin circular discs M and 4M having radii of A and 2 respectively are rigidly fixed by a massless rigid rod of length root 24A through their centers. So let me point out some important information which we are getting here is these. So this is a important information. The mass is M and 4M, and then we have the A and 2A, and the length is root 24, and their assembly is laid on a firm flat surface and set rolling without slipping. So the similar condition to our Irodov question, so that the angular speed about the x-axis is about the axis of the rod is omega. Yes, so that is, they have also denoted that in the figure. The angular momentum of the entire assembly about the point O is L. So this angular momentum about this point O is L. Okay, which of the following statement is or are true? Now coming to the option. Here first option says that the center of mass of the assembly rotates about z-axis with an angular speed of omega by 5. So this angular speed about the z-axis we need to find out for the center of mass. So look, this is a pure rotation about this z-axis. So here let me consider it like this. Okay, let me consider like this. This is x-axis, y-axis and z-axis. So about the z-axis it is going to rotate like this. I have also the video, you can watch this video. I have also created a short on that, so you can go through that. This is how it will look like. Just for the visualization I have created, don't waste much time on. Okay, let's go again here. So here this is rotating about the z-axis. So if omega z is something omega z, so can I say at any point's velocity, is can be given by omega multiplied by r. So that can be written down as omega z multiplied by r of any point. Now next thing is that this is also rotating about this. It is doing the rolling motion. So here this point velocity I can also give with this omega. This is omega. So this point velocity at this location, this point velocity I can also find out using this omega, which is omega multiplied by r. So let's write down this velocity. So I can say the velocity is, let's consider P point. Velocity of the P point is omega multiplied by r, which is omega multiplied by e. So velocity about this z-axis if we give from the rotation, so the velocity can be written down as v equals to omega r. So omega is omega z, and r of this point, look, they have given that this is root 24a. And this is A, and this is 90-degree angle. So of course this length becomes 5A, this length becomes 5A just from the calculation, right? So then this is 5A. So both velocities should be equal. So omega z multiplied by 5 should be equal to omega multiplied by E. A cancelled out, so omega z should be omega by 5. So now you take the angular velocity of any point, that angular velocity is going to be omega by 5. Now let's go to the second option. So first option is correct. Now the second option says that the magnitude of angular momentum of the center of mass of the assembly about the point O is this much. The angular momentum of the center of mass we need to find out. Now for the angular momentum of any point about a point is ICM multiplied by omega vector plus m r vector cross v vector, velocity of the center of mass. This is the formula for the angular momentum. Basically it is the angular momentum because of the rotation plus angular momentum because of the translation. The combination of that gives us the total angular momentum vector. Now if we look at this, so what is happening is we have the system like that. So let us first find out the location of the center of mass. So mass of this object is m, mass of this object is 4m, and we know from the geometry this distance is 5a. So I can say that the center of mass, the location of center of mass from the first object RCM is m2 r divided by m1 plus m2. So that becomes 4ma divided by 5, 4m multiplied by r divided by 5m. So it becomes 4 by 5 times of r, or this length, this distance, right? Now we calculated that this distance basically is 5a from here to here. So basically r is 5a, so that's why this becomes 4 by 5 multiplied by 5a, so that it becomes 4a, right? So this distance is 5a and this distance is 4a. This is the distance. So then I can say that let's find out the ICM multiplied by omega, the angular momentum about the center of mass plus multiplied by omega, and then m RCM vector cross VCM that we need to do. Now this is rotating like this, so I can consider it like this, a rotational motion plus the translation motion in that direction. So rotation is about this axis, the omega, so I can say ICM multiplied by omega. So ICM is basically about this axis I need to find out, and I know for a disk about the axis which is perpendicular to the disk, the moment of inertia I is mr square divided by 2, so that becomes mr square divided by 2. For the first one I1 becomes a square divided by 2. For the second one I2 becomes 4m multiplied by 4a square divided by 2, which is 16ma square divided by 2. So the total moment of inertia, because both of the discs are like this, so that's why the total moment of inertia of system is I1 plus I2, which becomes 17ma square divided by 2. So that's why the angular momentum about the center of the center of mass because of the rotation ICM omega is, let's call it as the L1, that becomes 17ma square omega divided by 2, right? Of course this will also have the direction of the omega, which is somewhere looking like this. This is the omega direction. Now next, the angular momentum because of the translation. Now this system is translating at this moment in this direction, so I am considering it like this: y direction, x direction and z direction. So at this moment this center of mass velocity is toward the negative x direction. So let me write it like this, the velocity is like this. So I can say that the r vector of the center of mass is 9a I cap, y 9a j cap. Why 9a j cap? Because this is the location of the center of mass from this point, so that is 5a, and this just now we calculated this distance is 4a, right? So this is 9a, and we know that this theta, this sine theta, from here we got it, sine theta is 1 by 5, right? How do we know? That is this perpendicular divided by this hypotenuse. This is sine theta. So sine theta is 1 by 5. So then I can say that the tan theta is 1 by root 24, right? So then I can say that the next, if this is this distance, let me take some other color. So this distance is 9a. Let's call this distance as z center of mass. So then ZCM divided by 9a is tan theta, and that tan theta becomes 1 by root 24. So that's why ZCM becomes 9a divided by root 24. So if I write down the position vector of center of mass, so that is 9a j cap plus 9a by root 24 k cap. That is the position of center of mass. Velocity of the center of mass at that moment is omega multiplied by r, and which is pointed in the minus I cap, which is omega about the z axis, which is omega by 5. So that is omega by 5 r is, look here, let me write down the r as well. R about the z axis. Look, I know the omega about z axis. So to find out the velocity of this point, the center of mass point, so find out this velocity of this point, what I'm going to say is that velocity is omega multiplied by r, right? Where r is the distance of this point, center of mass point, from this point, right, which is 9a. So that's why this becomes omega by 5 multiplied by 9. So this becomes 9 omega a by 5 minus I cap. This is the velocity. So now I can say the angular momentum is v equals that L2 equals to mass of the system, that becomes 5m, multiplied by r of center of mass, that is 9a j cap, plus 9a by root 24 k cap, and the cross product with the velocity, which is 9 omega a by 5. Just a little bit calculation, okay, don't worry, we will do it. So 5 cancel out, so L2 becomes minus of m omega a, and here is I cap, so j cap cross I cap is minus k cap, so that is minus k cap, 9a k cap minus k cap, and then there is, of course there is 9 here, and then there is 9a by 24 k cap cross I cap. So k cap cross I cap becomes the j cap, so that is 9a by 24 j cap. So this is angular momentum L2. So L2 becomes 9 m omega, and if I take out 9 outside, so of course it becomes 81. So 81 m omega a square, and then there is minus k cap, and this is j cap divided by root 24. This is L2 vector. Of course the L1 vector which we got is 17m a square divided by 2 multiplied by omega vector. Now let's write down fully in the x direction, y direction, like that. Okay, so here I'm thinking it like this, that let me break the L1 vector into the component. So L1 vector is of course pointed like this. If this angle is theta, we have calculated this theta, so this sine theta is 1 by 5, so then cos theta is root 24 by 5, right? So then there will be two component of this L1 vector, one in this direction, another in this direction. Okay, so L1's component in the, here I am taking this as y axis and this as the x axis. So L1 will have two component in this direction. So there will be two component, one in this direction, another in this direction, basically negative z direction and negative y direction. Okay, so when I break it this, we need to understand it in the 3D. This is the angular momentum pointed like this. This is the theta. So then this component is L1 cos theta, L1 cos theta, and this component becomes L1 sin theta. L1 vector is L1 cos theta, which is 17 m a square omega by 2, and cos theta is root 24 divided by 5. Okay, and that direction is minus j cap, so that becomes minus j cap. Then there is next part, the L1. So L1 sin theta, so that is 17, again negative 17 m a square omega by 2, and the omega's component in that direction becomes, what is that, 1 by 5, and that is k cap. So basically L1 vector is, let me simplify it if I can. So then we are getting 17 m a square omega by 10 multiplied by root 24 minus j cap and minus 17 m a square omega by 10 k cap. Okay, so this is L1 vector. L2 vector we got it here. Let's add both of them. So L1 vector, the L net vector about the O point is L1 vector plus L2 vector, so that becomes the L1 vector. L1 vector is this value minus 17 ma square omega by 10, and then you have root 24 j cap, and then you have minus 17 ma square omega by 10 k cap, and then you add the L2 vector. So L2 vector is minus 81. Okay, so there is minus 81 m a square omega. From here I am writing, okay, m a square omega, and minus plus k cap, so and there is j cap, so j by root 24, and minus plus 81 m a square omega k cap. So finally we have reached up to this, and now we need to reconcile it. So here is m a square omega is just a constant, and then we can take out each common from each term, and then we have minus 17 root 24 by 10 minus 81 by root 24, and then there is j cap, and then there is minus 17 by 10 and minus 17 by 10 plus 81 k cap. Okay, this we are getting. This is the angular momentum. If we calculate this value, I think we will not get anywhere close to this 81 ma square omega. Nowhere we are getting 81 ma square omega. We could have got it if we somehow have cancelled out the other terms. Okay, like let's suppose only this term is remaining, other terms are cancelled out, then only we can get this answer, right? So that is not happening, so that's why that second answer is incorrect. Somewhere we are getting something else about this O point, so that becomes incorrect. This is correct. Now let's move to the next point. Magnitude of angular momentum of the assembly about its center of mass is, so this value, is it this or not? So look, here we have done this calculation. This is the angular momentum, 17 ma square divided by 2 omega vector. This is about this, here we did L1, yeah, this one. So this is the angular momentum of the center of mass. So angular momentum of the assembly about its center of mass is 17 ma square omega divided by 2, which is correct. Next, magnitude of z component of L vector. So z component of L vector, and they have said that the L vector is basically the angular momentum about the O point. So basically we need to again go to this answer and just look at the z component. This is the z component, right? It says that it is minus 17. So let's just simplify the z part. So minus 17 by 10 plus 81, so that becomes 810 minus 17 divided by 10, so that becomes that value is 793 divided by 10, and then there is ma square omega. Of course omega here is that just omega, not the omega vector. So I about the L about the z axis, or along the z axis about the point O is 793 by 10 ma square omega. This is, which is again 79.3. okay, and here we get it 55 ma square omega, so that is incorrect. So now look, there are the other methods which have been explained, the other videos on the YouTube. I have seen that videos, but I thought of explaining it using this simple formula. Of course for you it may seem like a tough calculation, or little bit my calculation may be incorrect somewhere in this, so please pardon me for that. And you can again go through that the concept which I have covered here, but this is a very nice question which gives us idea of lot of the concepts how we are going to apply, which will help us to understand better. So it might seem for some student like it is just a waste of time covering this advanced question, but I think it is really important. You should cover this, and you just not cover for just sake of covering, understand the concept inside it, which is very important concept. How do we consider the angular momentum of a body which is performing a rolling motion, and simultaneously it is looking like it is doing the two rotational motions. So thank you very much for being tuned to this question. And if you want more questions, then of course you can drop the comment, and you can also watch the other videos. You can also share with your friends. Thank you very much.